Let's start this up. So, oh, I guess before we start, I'll show you guys. What I posted, I feel like it was yesterday, last night maybe. Okay. Blah, 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 blah. Okay, so last night I posted this general methods document, both the RMD and the HTML, so you can have a look. I need to give you the RMD, probably generate it yourself, but just to see. So if you just want to have a quick look at this document, right? And so here, because in chapter 5, right, we established all these methods that we've got for any sort of Anova situation. And so I kind of went through, I broke them down into many, many subsections, basically a summary of chapter 5, right? And so first thing you're going to do is you're going to plot the data, and I've written out what we're going to look for and things like that, and then figure out if we need to re-express the data, right, through transformation. There's a couple of sub points here. Then if you transform the data, or if you don't need to, then you can run the Anova. And once you've got your model, right, your Anova model, then you can do a residual analysis, right, to make sure that your model fits well. And then depending on the question, if you've got a specific question in mind, right, maybe you don't have to look at the individual treatment effects, right, the one-by-one treatment effects. Maybe you're only concerned with a specific pairwise comparison, then you can skip straight to here. So this is the general kind of everything that you could do with Anova, and just the general methods. And then, of course, you can draw your conclusion just kind of depending on what your research question is or what the answer you're trying to get at is. I use the Words with Friends data, which is the same as the case study, but I did all of the things, even if they weren't necessary. Like, we didn't need to do a transformation, but I showed you how you would determine if you need a transformation, right? And so I've got all my code in there, and you can just kind of follow along, especially for lab 4. You're basically going to do this, but with your data, right? And so just to see how things are done. As always, this may not be the most clever way, it may not be the most elegant way. I always just try to show the simplest way possible, right? And so I try to boil it down to make my code as simple as possible, and then you guys can take it and run with it and do cool stuff and find new packages and do all those cool things. But I've just kind of done the very minimum that you need, right? So so you can have a look at that when you're working on your lab 4, just to see what's going on. And oh yeah, and I posted the solutions to lab 3, but I'm pretty sure I mentioned that last day, right? So you can have a look. Oh, one cool thing that I don't think I've mentioned, and I use it quite a bit. I know it's at the bottom here. It doesn't open the RMD file, but that's okay. We can still read it, right? And so if I want to reference something that I've saved up here, right, in our code, if I want to have something called lower, for example, and then I want to use that number in my text, right? Notice that it's hard to see because we're not in our studio, right? So it's not blocked up. But notice that here, right, this is the end of my R code chunk, and here I start writing about, say, we're 95% confident, blah, 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 blah. And then the interval from, and then if I do a little tick, right, and then an R, it says, okay, now I'm in an R environment, and now I can call an R command, right? I want to round the lower to 1 decimal place and then close it with a tick. And that's how I can bring in values and kind of make my text as well, kind of incorporate values, because sometimes I'll just read the output and type in the output if I'm being lazy, right? But if I'm being very proper, I should, whenever I talk about a number, I should be referencing a number that I've calculated, right? And so that's something that you can maybe start kind of incorporating. I think you'll find it pretty useful, right? Because otherwise, you know, you forget to remove a data point or something, and then you have to change all your numbers, and it's just kind of messy, right? And so so that's in there for you to have a look at. Cool. All right. Any questions about that before we get started? Nope. Okay. So like I was saying, last night I was like, oh, I've got chapter 6 pretty much on lockdown in my brain. I don't think I need to write down any notes. And then this morning I kind of, I'm going to write down some notes just in case. And then I ended up with just so many notes. It's crazy. Usually for our classes, I have like 2 pages of notes. Here I'm like, oh. The funny thing is there's not a lot going on in chapter 6. So we're going to start chapter 6. The only difference is that now we have blocks, right? So now we're talking about more than one treatment, sort of, right? We've got more than one explanatory variable. In fact, we're going to talk about 2 explanatory variables. Okay, so chapter 6 is on blocking and two-way Anova. So the scenario that we have, again, is that the response is numerical. Yeah.
Usually we use Anova experiment.
Yes.
But we are doing observation study. Blocking is similar to filter.
Yeah, so we'll talk about, there's a couple of different ways that we can block, but essentially you block an experiment or even observations if you want to eliminate variability, right? And so think about a paired t-test, for example, right, where I've made multiple measurements on the same subject. Then to eliminate that subject variability, right, or kind of say, okay, well, if this person's really slow to start with, they might improve, but they might still be really slow at the end, depending, like a running experiment or something like that, right? And so we eliminate that type of variability between people if we could do the pairwise comparisons, right? And so blocking does the same thing, where we kind of group like things and give each of them the treatment, right? And so we do the treatment on each of these blocks. And so males and females, right? We could block on males and females if we think that gender might have an effect on the treatment, right? Things like caffeine, males and females are affected a little bit differently by caffeine, right? And so we would probably block on the gender and say, okay, well, these females get, you know, these treatments, these males get these treatments. We're going to be kind of focusing on a very specific situation where a block only gets one of each treatment, right? Which is a little bit different from, you know, the 2 sample t-test or paired t-tests that we've been looking at before. But yeah, so here we go. But that's the only thing that's different. Everything that we learn in chapter 5 still applies. We just need to make room for another explanatory variable, essentially, right? Another categorical variable in there, which is the blocks. So the explanatory in this case, is going to be 2 categorical variables. These categorical variables, the explanatory variables, we often call just factors in general, right? So instead of calling them explanatory variables, we just say we have 2 factors. 2 categorical variables, 2 factors. And so now, right, and that's where the two-way ANOVA comes from, right, is that we have 2 factors to deal with. And so two-way ANOVA we have 2 factors. Right. In chapter 5, we were dealing with just the one-way ANOVA, which is essentially the simple regression equivalent, right? Just one explanatory variable. Now we're moving to two-way ANOVAs where we have 2 factors instead of just the one. Right? So we're expanding a little bit. Okay, so 6.1, I abbreviated the names of these sections because they were really wordy, is essentially on blocking. I'm just talking about blocking. One thing to keep in mind about the blocking isn't going to be the treatment, right? There's going to be some bigger treatment, some bigger thing like a drug or exposure to something, right, that we're interested in. The blocking is just to minimize variability. Okay? And so we block to try to minimize the variability right within some factor, right? So whether that be gender or where you live or just kind of things like that. So within some factor. Much like the paired t-test, right, where we're trying to eliminate the fact that we've got 2 measurements from the same people, and so that person is going to track against the before and after measurement, for example. Right? And so, for example, a paired t-test is blocked, and I'll put blocked in quotes because it's just the way to think about things, is blocked on each subject. Each subject gets both treatments. Each subject gets both treatments, whatever they are. If we're only talking about 2 treatments, we can probably make do with just the paired t-test, right? Or some sort of t-test. So for ANOVA, right, we're talking about more than 2 categories, so 3 or more categories. And so now we've got kind of more than 2, and we talked about it last day where we could go through and do, pairwise comparisons, but that's not what we want to do because it exposes us to type 1 error, blah, 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 blah. Right. So we block to try to contain kind of like things with like things, right? And do comparisons on apples to apples, for example. And so we can block, we can block in 3 ways.
There are 2 types of selecting same sample.
So a paired t-test should, in general, just be 2 measurements on the same subject. Sometimes you can argue that I've made a pair that I could treat as the same subject, right? Married couples, for example, they're not necessarily the same, but they're in the same marriage, right? So they're paired on that marriage, depending on what you're talking about, right?
In this class, I'm selecting 5 people at random.
Mm-hmm.
After and before, I select the same 5 people.
That's right. That's right. Yeah. So for a paired test, right, then we would do, okay, you get before and after, and then whatever the treatments are, right? Sometimes everyone gets the before treatment and then the after treatment if you're doing some sort of improvement study. But if you're doing a comparison of, you know, a placebo versus a new drug, then you would randomly select who gets the placebo first and who gets the drug first within your sample. So 3 ways to block. The first way is to subdivide. And it's a little bit kind of funny to think about because all of this kind of blocking and everything came from agricultural experiments, right? Where they've got an actual plot of land that maybe, you know, this side gets more sun than this side of the plot, right? And so you don't want to put all of these seeds over here and then the next treatment over here, because then there might be an effect of where the sun comes from, for example, or maybe, you know, it gets more water in some sections, or maybe the soil is just better in some sections, right? And so we've imagined this huge plot of land, and what we want to we have, you know, 5 different treatments that we want to look at and compare. So what we do is we divide our plot of land into blocks, right? And then we put our treatments in each of these blocks, right? And so what we get, if we imagine kind of, here's our plot of land, 1, 2, 3, 4, 5, let's say. So here's our plot of land. And let's say the water is somewhere down here, right? That might affect how things grow. Let's say we're growing tomatoes. I don't know. I love tomatoes. And then the sun is somewhere over here, right? And so maybe this section is really dry and this section is really wet. And then somewhere in between, the soil's pretty happy. And so we've got good soil here. Just kind of imagine that kind of scenario, not that hard to imagine, right? And so what we would do is, instead of planting all our best seeds up in this section and then moving down, and we've got our lesser grade seeds down here, and then our next grade seeds here, and then here we put our worst seeds, but somehow they generate these huge plants because they're close to the water and the fertile soil. What we do instead, right, is, so now we've got these blocks. If we're looking at 5 treatments, let's see if I can draw 5. Dun, dun, dun. 1, 2, 3. Not bad. Good, not great. Oh, whatever. Doesn't matter. So now here, right, I'm going to have my treatment kind of broken up here. So within each block, right, I'm talking about, I've got 5 treatments in this hypothetical situation, right? And so I've got 1, 2, 3, 4, 5 treatment spots within each block. Right? So what I do is I randomly assign, okay, here goes my best seeds, here goes my next grade seeds, here go my next grade seeds, here go my blah, 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 right? So for each block, I do a random assignment of which seeds go where, right? Because now, as long as I'm randomly assigning within each block, right, I can be more confident that I've got kind of a good mix and I've eliminated where in the plot I'm planting as a factor, right? We use that in real life too, where we say in real life, not just in stats, in fake life. In real life, we say, oh, well, that's going to be a factor that I need to consider, right? And so, right now we've eliminated that because we've randomly assigned, and so hopefully what we're kind of aiming to do is we're eliminating the position within the plot as a factor. So if we've got, you know, treatments A, B, C, D, E, A to E, then we might have C, A, B, E, D, Cabed, Bedka, not random, right? But et cetera, where we just randomly assign each treatment to each block. So each block is randomly assigned words matter, don't they? Each block is randomly assigned. What did I want to say? Each treatment is randomly assigned in each block. But also I wanted to say that each block gets every treatment once. So which one do I want to say first? I think I don't want to say that. Each block receives, I did a I before E, receives, except after C. Receives each treatment once. Treatments are randomly assigned. That's what I wanted to say. Within each block. What we're trying to do here, right? This should hopefully eliminate kind of the blocking as a factor. And it'll still be there because it's taken into account, right? But it's not some sort of unknown. We're presenting it and saying, hey, I've captured this blocking. And so now, right, blocking helps eliminate the blocking factor, whatever it is, right? Whether it be where in the plot of land it is, right? Or what gender we're talking about, or kind of where you live. So blocking helps eliminate the blocking factor from the treatment effects. Because now, right, I've got them all kind of spread out and I've randomly assigned where they're gonna go. And as long as I make things random, right, that's all I can do. I've done my best. So that's the subdivide. This really only works in experiments. Right? I don't really see how we could say, okay, you're gonna go live over here and you're gonna go live over here and then report back to me in 3 years how you feel about where you live or something like that, right? We can't do that. And so, so subdividing is really just for experiments. Another option, did I number these? I did. Is to sort different characteristics, right? So now you're matching characteristics and putting them in the same block. Okay. Sort by characteristics. And it's tough, right? Because we're being pretty vague here. It depends on the scenario, right? But you want to sort on characteristics, for example, where you live, right? That might be something that you want to block on. So sort by characteristics. To create blocks. With similar characteristics. So this would be more for observational studies. You could probably still do it with experiments, but experiments you have total control, so you'd probably go the subdividing route where you control everything. So sorting is, I'd say, more for observational studies, where you say, oh yeah, you live in the Upper Mission, right? How you feel about driving around in Kelowna might be different from how someone downtown lives or feels about driving around in Kelowna. I don't know, something weird like that, right? And so, so then you're essentially creating strata, right? But these are your blocks now. Remember, you're still assigning treatments to each of these. So it'll still be kind of a pseudo experiment, right? Whether these blocks are created by you or kind of naturally occurring, that depends. Or our third option is the one that's similar to paired data, right? But now we've got these multiple measurements, right, where each individual or each subject gets all of the treatments, right? Not at once, but they're exposed to each of the treatments. And so we can reuse data in the sense that each subject is given each of the treatments so then the subject is the block. For example, in paired t-tests, right, we said the same subject gets both treatments. Now we've got more than 2 treatments, and so now we can extend that, right? But it's the same repeated measures type of situation. And so we call this repeated measures. Or we've made repeated measurements on the same subject. you'll want to be on the lookout for things like carryover effects, right? And so if you give someone, if you randomly assign them something between, the example in the textbook uses a placebo, caffeine, and basically chocolate, right, to see how they're affected. And so if you gave everyone the placebo, and then you gave them caffeine, and then you gave them chocolate, right, then that's not very good, right? We want to randomly assign the treatment that each subject gets, the order of the treatments, right? Just the same as we did up here with the blocks, right? So now our blocks are each of the subjects, and let's say we've got the three treatments that we're talking about, right? Instead of 5, we want to randomly assign them, but we want to be on the lookout for potential carryover effects, right? If I give someone caffeine and measure, you know, how fast they can do something, and then I give them a placebo an hour later and measure how fast they can do something, right? We've got that carryover effect that we need to take a handle on, right? Because the caffeine is probably still working, right? And so what we do, right, is we make sure that there's enough time between each of these measurements that we can say, okay, well, the measurement they had previously should be independent of the measurement that they have now, right? And so on and so forth, right? So we want to space them out just to avoid carryover effects. One concern with repeated measures is carryover effects, which should be addressed in your design, right? In your study design. Which should be addressed in your study design. There's one example in the beginning of the chapter, and it actually made me laugh because I thought it was so funny. It ends with hand over the grant money. Anyways, it's on page 258. It's kind of long, so I can't read it to you. But so anyways, they submit this this grant proposal where they've designed a study, and it's kind of a back and forth between someone who approves these things, and they say, no, that's not going to work because your variability is going to be too large because you're not controlling for this and this and this, right? They resubmit the grant proposal, and they say, okay, we're going to block on this, right, to control for that variation, and hand over the grant money is how it ends. I think it's pretty funny. So, not really. Well, I think it's helpful to kind of explain what's going on, but funny textbook, funny. All right. So those are our 3 styles. Either way, we're going to have a blocking factor and a treatment factor, right? And so in general, right, there's going to be one thing that we're interested in, right? That's the treatment factor. And then we're going to block if we have to, right? And so for two-way ANOVA, we have 2 factors. The first one is going to be the treatment factor. That's the one that we're interested in. This is the variable of interest. And our second factor is going to be a blocking factor. Just to eliminate some of that variability. Okay. Any questions so far? All right. Okay, okay. He's taking a pass. 6.2.
So, in the two-way Anova, you would have your F values and P values, right? And,
That's right.
So what happened if both are significant? I mean, treatment factor and blocking factor.
We get there in, I want to say 6.5, but so it's a very slow moving chapter because nothing, well, things are going on, right? We've added this additional thing of the blocking, but things haven't changed that much, right? And so, but to answer your question, spoiler alert, it means that your blocking is doing something, right? It means that it's, so your treatment, if it's significant and your blocking is significant, right? It means that you really need those blocks, because otherwise that variability is gonna kind of cloud your treatment. So I would think of it as kind of, okay, you've effectively sorted out kind of that noise, right, of the blocks. And so putting things into blocks really helped you to figure out, hey, what's actually going on with these treatments? Yeah, yeah. I would try without the block and see if you can have a simpler model, right? We're always going for a simpler model. And so if you run it and the blocking is not significant, but the treatment is, right? Maybe try removing the block and see what happens. Even if the blocking is not significant and the treatment isn't, I would still try it just to see what's going on. Depends on the scenario. Right? Cool. It all depends on the, well, it depends on the data, right? So because this is such a broad scope course, I mean, we could be talking about biostats, econometrics, all these things. It really depends. Not helpful. No. All right. So 6.2, I've abbreviated because it had, I think, a really long name. Exploring data from block designs, or maybe I stole it. Exploring data from block designs. So chapter 6 just kind of slowly takes us through each of those steps that we outlined in that general methods document that I posted. Right. First thing we're gonna do, well, is figure out what our blocks are, right? Then we might plot things, and then, so here we're gonna get into the plotting of things, and then we look, okay, can we transform the data? Right, so far we're essentially following those exact same steps as with the general methods that we posted, right? So, so we look and see, you know, does this look good? And then can we do a transformation? Should we do a transformation? And then we actually run our Anova, figure out what our residuals look like, assess our Anova, right? Assess the model fit using residual plots, and then we can draw our conclusions. So it's going to be the same, but all of those, I don't know how many sections that makes, but it's going to be chapter 6. Yeah. So now if we go into just kind of exploring data from block design, so we're not even analyzing things yet. We're just at the beginning stages. So for a two-way ANOVA, we use what's called an additive model, right? This treatment plus this block plus this overall average gives me my output plus the error, right? Gives me my outcomes, my observations, words. And so we will ultimately, and we're not quite there yet, but we kind of have to know what our model looks like. So we will ultimately use an additive model for two-way ANOVA. So what that looks like is you've got your observations or your responses here, y, which is going to be mu, your overall mean, plus tau, kind of a fancy T. How good are you guys with Greek letters? Pretty good? This is tau. Tau. Tau is going to be the treatment effect, right? And so before we were using alpha as the treatment effect, right? But that's because we only had one. Now I want to specify which one's my treatment and which one's my block. And so you can still use alpha if you want to. I'll know what you mean. But typically if you're reading papers and things, they'll probably use tau for the treatment. And so here, this is the treatment effect. Plus beta. This is a different beta from regression, right? Because this is the blocking effect. Uh-oh, I'm running out of room here. It's okay. This is my blocking effect. And then plus the errors, everything else, right? Because these are my observed responses. So my model, right, when I'm fitting things are going to be this section, right? U plus tau plus beta. Those are going to be my fitted values. What happens is, okay, if we didn't have a blocking effect, right, and we only looked at mu and the treatment effect, if this guy is really big, it would have to get absorbed into the errors, right? And so that inflates my errors. And so that's why if we can tease out the blocking effect, then our errors become a lot smaller, right? And so then we've got better estimates and so on and so forth, right? And so now they've used that, the analogy of the CAT scan, right? Where you send a body through and the first thing you see is the skeleton, right? So the skeleton, I don't actually know how things work. I'm just going by the book. The skeleton would be here, right? And then we add on another layer of maybe muscles. Sure, muscles. Great. That's the next important thing. And then we add on another layer of skin. Great, cool. Great. Organs, I guess? No. Yeah, yours are both. Right, and so we've got these layers of things and things. Of course, we could have more than two things. We're not going to go there, right? We're going to stop here. This is usually sufficient, right? We don't need to have this huge elaborate thing, right? We can usually kind of stop at, okay, we've got an overall mean, and then we got the treatment. That's where we were looking at in chapter 5, right? And then we just had the residuals on top. Now we're adding on that blocking, which is going to capture more of those of those effects, or shouldn't say effects. It's going to capture more of the blocking effect, right? But it's going to capture more of that variation, leaving the residuals to only capture the kind of what's left over.
Treatment effect is same as the treatment effect.
Yes.
Different from
Yeah.
your overall.
Exactly. Yeah. So the treatment effect, so this portion we've seen before, right? This would be the one-way, essentially a one-way ANOVA, right? We used alpha instead of tau, but, and you still can, like I said, but notice here, right, that we have this additive model, this plus this plus this, right? So we're adding things on top of each other. What might happen, right? So this is the model that we're going to work towards. What might actually happen is that the treatment and the blocks might be multiplicative, right? Meaning, okay, if you're in this block, then you're 3 times more likely to have this effect, right? This treatment effect. If you're in this block, you're 15 times more likely to have this effect, right? Effect. And so this,
So it's like adding weights to your blocks.
adding weights to the blocks. Yeah, kind of. But we can correct it. Yeah. So yes, but let's say, so what I'm trying to say is that this is an additive model. Okay. So what if we had something what if we were seeing in our data something like y is mu plus tau beta, right? Plus the errors. To tease out the tau betas, right? Doesn't really work because we've got this mu, so maybe it's the mu times tau times beta. Move it over. Just imagine it for a second. Now, this would be a multiplicative model. But we can get it back to essentially an additive model by taking the logs, right? Remember the log laws, if we're multiplying, then what can we do? Then if we're multiplying inside, it gets added out, right? And so if we think about just taking the log of mu tau beta, that's going to be the log of mu plus the log of tau. Oops, tau keeps having a weird tail there, plus the log of beta, right? And so now we're back to an additive model. So that's going to be the reason why the log transformation is often our go-to, right? Because it has this property of kind of straightening things out, right? We get back to this additive model, even if we've got this. Basically, you can think back to the interaction term, right? Where we're saying, okay, this interacts with this, right? And so, so if you've got this kind of multiplicative model, then you can straighten it out to an additive model by taking the log. So
This one lead us to the same additive model we have used initially.
no, it won't be the same, but it'll still be additive. So then how we interpret it can be the same.
So it's like if you're going with this additive model, it's like change in the mu. change in the tau, change in the blocking effect,
Yeah.
right? Like log is like change in the values.
Yes, but
That's marginal.
yeah, so you'd have to remember that you have taken the logs, but as far as kind of how we interpret the overall p-values, right? Like ultimately we're working towards p-values, right? How we interpret those are going to be the same, right? So the log of the effects has some sort of significant effect, right? The log of the blocking has some sort of significant effect, right? But we're also logging our responses, right? So everything's being logged. Cool. So how do we know if we need to take the log? There's a new plot for us to do, and it's called the Anscombe plot. Okay, so to assess whether an additive model is appropriate we use an Anscombe plot. There's actually going to be more than one. So maybe I'll just say we use Anscombe plots. Cheating. So what we do is if we let our block be X and our treatment be Y, what we do is we make XY plots, so we make scatter plots of each of these XY combinations, right? So there's going to be block number 1 with treatment number 1, or treatment A, block number 1 with treatment B, that kind of thing. And so we make scatter plots of all XY combinations. And if I had heard about this plot before, it certainly did not stick. I was like, oh, that's a new plot. Never heard about that or used it, or I must have, because I did do a course very similar to this one, so I don't know. Just didn't stick, I guess. So no, I'm learning from my mistake, or from my teacher's mistakes. So now I'm not sure it's I mean, it's important to be able to say, okay, the additive plot is appropriate because that's what we're using. It's just another tool. Okay, so what we do is we make scatter plots of all the XY combinations. And so if we find parallel lines, right, meaning that all these lines have just the same slope essentially, right, then we can use an additive model, right, because things are increasing at the same rate for each of the blocks in each of the treatments. So if we find parallel lines the additive model is appropriate.
because you.
How about I steal the image? I'll go find it because it'll be easier to see if we, I think it was way back here somewhere. Where am I? I feel like that's topic 8.7. Come on. Of course, I didn't make any notes here. 6.2. Where are these Anscombe plots? Ah. Okay. There's another one. This one, I think. This one. I'll put it in here and just kind of. In fact, can just kind of talk around this one. Because that's what's going on down here, right? And so what we said, if we've got parallel lines, right? And so that means that we can use this additive model. Right? Whereas if we've got if the lines have different slopes, we need to transform the data using logs, right, to get an additive model. We need to transform the data using logs, right? Usually natural log. Is it for, I know for sound and just kind of that kind of stuff, we use base 10, but I think for concentrations, I think they also used base 10 in one of the examples. Sine and cosine. Well, that's to model cyclical things, but to transform something that behaves like that, then you can use log base 10. But for everything else, we use log base E, right, the natural log. So if the lines have different slopes, in fact, if you use log base E all the time, it's not really gonna bite you in the butt too bad. So if the lines have different slopes, we need to transform the data using logs to get an additive model, which we just showed.
Each line represents one block. One wide.
Yeah, so in this case, yeah, there's 4 blocks. We've got the response here and the treatments here. Perimeters, but this isn't actually the perimeters. I feel like this is, they're modeling. You're asking the tough questions now. I know.
When we see parallel lines, we interpret as there is nothing going on. general. It's just the magnitude is increasing.
So yeah, so we're not saying that nothing's going on. It just means that our default plot of the overall mean plus the treatment effect plus the blocking effect plus the error is good. Like it'll work just fine to model this, what's going on here. Right? Here, what we're saying is that, okay, for these guys, things are increasing really quickly, right? Whereas for these guys, things aren't increasing, you know, quite as fast. So then we have to adjust that by taking the logs. I knew these would be, we'll have to look at how we plot them, because I'm not really wrapping my head around. It's the XY combinations. These are the blocks. So we've got 4 blocks. So far, so good. It's confusing because we're looking at the width and the length of a rectangle, I think it is. And then here we're modeling the perimeter, right? So our output is the perimeter. Whereas here, we've got, again, the length and the width of a rectangle, but we're finding the area, right? If we think about the perimeter, right? The perimeter is just the length of each of the sides, right? This side plus this side plus this side plus this side. Right? So then we've got this additive model of 2 widths plus 2 lengths, right? Here, if we're talking about the area, right? If we're doing the length times the width, then we've got this length times the width multiplicative model, right, for the area. And so that's why we get this type of scenario. But each of the colors are its own block. Would have been nice if maybe they had used a legend would be nice. But also that we weren't looking at a square maybe, because it looks like the width and the length are always the same, which is confusing when we're trying to tease out what's going on here. But okay. We'll move on. I know there's questions because I have questions, but we'll leave them for next day. I'll look into it, see how these things are actually plotted, and then we'll have a better idea of what's going on. This is what we look at. This is what we look for to make sure that we can use this model that we're about to use. But if we get a plot that looks like this, right, then we know that we have to take the log, right, the log of the, yeah, or the, probably just the response, now that I think about it, but also something I should clarify before I say anything.
And after you apply the log, do you expect the length to be
Yeah, they should kind of even out and stack out. So it should look more like the one on the left once you've taken the logs. And that's why I think it's just on the response, because otherwise you're doing it on everything, and logs kind of behave that way where it might straighten out, but I think it might just be the response. Something for me to look into.
The orange line seems to be a reference point.
Yeah, did we look at, I think you might be right there. It definitely looks like, and I think we only looked at 3 different. Yeah, you're right. It's just a reference line. Anscombe plots. It is a reference line. Put that on here. There.
So, for my understanding is the reference point, the reference line is what would you expect the data to behave?
Yeah.
And then if it is parallel to the reference line, then you have
That's what it that's what it looks like to me. Obviously, this is a perfectly additive model, so we will kind of expect some changes, right? Because the perimeter of a square is very consistently depending on the length and the width, right? And so here we've got this perfect thing going on, and I'm guessing that's why we would have the reference line, because that's kind of what we're, as long as we're kind of looking for some slope around that, right, then that's good, right? Whereas clearly on the right, we don't have anything close to that reference line. Good. We'll look at the code, I think, next day, just to kind of see what's actually going on. How do we make these darn things? So we'll kind of parking lot Anscombe plots until I've dug a little deeper. How about that? Fitting the model, we can do that. 6.3. Fitting the model. First thing we're going to talk about is there's two ways that we can arrange our data, right? Just kind of figuring out how we need our data arranged for our analyses. And it's going to depend on what we want to do, what we want to say, right? And so we say we've got this tall format, right, where we've just kind of stacked everyone on top of each other. And then we've got this wide format, which is the one that we're going to use for Anova, right? But it's good to know that we can arrange our data in two ways. And there's packages that do this for you, right? And so, is it called Melt? And I think you can melt the data into tall format, and then I can't remember what it's called when you bring it back up to wide format. But I might be wrong, but I'm pretty sure it's another Hadley-Wickham package. So it's been a while, but it's out there. Right, so it'll just do it for you. All right, so if we want our data tall, and I'll just do the first couple of rows here, we have case 1, 2, 3, 4, 5, 6, da 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 da. In general, we have block, and let's say we have, you know, blocks A, B, C, D, allowing for however many we need, right? And so, and then let's think about, okay, we've got, let's say 3 treatments, X, Y, Z. And so we've got a treatment X, Y, Z. Each block gets each of the treatments, right? And so block A must get treatment X, Y, Z. I'm gonna give myself a little bit more room by scooting this over just a bit, because I also need to put the response on here. I'm just gonna dot it because it depends on the situation, right? But you're gonna have a response for each of these combinations. And then block B gets X, Y, Z. And so on and so forth. That would be your tall data format, where everything's just kind of cascaded down on each of the blocks, right? Because now you've got one row per treatment and response, right? And then you've got this other category of the blocks. The format that we need is the wide format. So we use wide format in Anova. Oh, glitched out. There. So this is the format that we're going to use when we talk about the theory and stuff. And of course, R doesn't need you to rearrange it into the wide format. It'll just do it internally, right? But let's have a look. So what we have is we put our blocks on one of the axes and the treatment on the other axis. Not making a graph, but a table, so I'll put it in the columns and the blocks in the rows. And if I've got treatment X, Y, and Z, then my blocks can be A, B, C, just for example. Maybe D, just so we don't have a 3 by 3. So what we do, if we had to calculate all these things by hand and just kind of get an idea of what's going on, of course we don't, right? But it's helpful to know what's going on internally, right? And so we've got 4 blocks, A, B, C, D, and then we've got 3 treatments, X, Y, Z. What we do is, so each of these little cells, right, are going to have some outcome. Right, YAX, YAZ, oh, sorry, that doesn't make sense. YAY, YAZ, yes, and so on and so forth. In general, right, if we have, do we use J blocks and I treatments? I mixed these up, didn't I? Should be YIJ. Doesn't really matter. Can mix them up later. But what we have, right, is YIJ is the response at block J and treatment I, right? So I ranges from 1, 2, 3. J ranges from 1, 2, 3, 4. Right? And so we can do these combinations. So this is the response at block equals J and treatment equals I. if we want the average across all the treatments, how we denote that is we use y bar I period, right? This is the average across all treatments. Average across all treatments. Y dot J bar is the average across all blocks. And if we do y bar dot dot, that would be our overall mean. Y bar dot dot is the overall mean. So I guess I should have put my, should I clean it up now? Because we like to read I as the rows and J are the columns, right? Is it okay if I change my table?
Yeah.
It's my table, I'll do whatever I want. There. I'm just changing. Now I have 4 treatments and 3 blocks. That's okay, I've got a general table anyways. So now I've got a treatment. I've got I treatments. A, B, C, D. And J blocks X, Y, Z. So now, to add to this, what we can do is we can find the average across each row, right? So here, this is Y bar. The first treatment is A, but I'm just going to use one dot, right? That would be the treatment average for treatment 1, right? Across all those blocks. And then I've got Y bar 2 dot, Y bar 3 dot, and Y bar 4 dot, because I've got all these averages.
If the averages are same, then blockings are not doing anything.
Yeah, well, the blocks. Good question. Because the blocks could be doing things, but in different directions. So I think, good question. I'll have to think about that one a little bit. But then we can do the same thing down here, right? We can find the average across the blocks. So I guess I'll use green again. Now I've got Y dot 1 bar, Y dot 2 bar, and Y dot 3 bar. Those would be my column averages across all the treatments. And then at the intersection here, what I've got is the overall mean, Y dot dot bar. So And I know I'm cheating. Make room for one more line. Because what we're going to have here is we're going to use these averages to figure out what the effect of each thing is. And so the effect is going to be the average from that column minus the overall mean. Right? That would be the treatment effect of group 1 from the overall mean. Right? And so now we've got this effect, which is y1 dot bar minus y bar dot dot. So if we keep going, y2 dot bar minus y bar dot dot, y3 dot bar minus y bar dot dot, and finally y4 bar dot minus y bar dot dot.
Not necessarily to be positive value.
No, they can definitely be negative, right? If we've got this negative effect of the treatment, right? It goes down from the overall mean. And because it's a mean, we're kind of expecting it to be a little bit kind of even around. Right? So here, these are my treatment effects. Right? All of these. So these are my treatment effects. We can do the same thing for the blocks, where we subtract the overall mean again. And so we get y bar dot 1 minus y bar dot dot, y2 dot 2, sorry, y bar dot 2 minus y bar dot dot, y bar dot 3 minus y bar dot dot. And this is going to be our blocking effect. So we can go through and do this, right? We're not going to break it down, but and do this by hand. Right? We're going to use R to do this, but it's good to have some idea. I know, can you imagine?
We'll be lost in dots.
Yeah, there's so many dots. Yeah, was it a dot there? No. Right, so, but the overall idea of the effect is the same, right? We haven't seen it like this before, right? But we looked at each treatment. How far is it from the overall mean? How far is it so how far is each treatment from the overall mean? And that's your treatment effect, right? Now we've just got the blocks, and so we need to look at the block effect. Okay, so our fitted values, what time do we have class till?
Yeah.
We're way over time.
Yeah.
You guys, you're too good. You guys are just quiet.
No, it's interesting.
Well, I don't know if it's 7 minutes overtime interesting. I'm so sorry. I was like 10:57. I don't know. It's like, do we go till? It's like, I must have about 20 minutes left. Not today. Yeah. Okay. My apologies. My apologies. Yeah, but I'm not sure that's the point.